With electronegativity, we can anticipate the relative electron densities of two atoms that are bonded to each other. So which is going to be more delta plus and which is going to be more delta minus. Organic chemists, however, are particularly obsessed with one element, namely carbon. So one of those atoms is always going to be carbon that we're looking at, and it has an electronegativity value of 2.5. But we're going to look at a variety of elements for the other atom. We're going to give that the letter X. It's generic. Sometimes it's a bit more specific, meaning just a halogen, but in this case we're just talking about any other heteroatom. And the first one we're going to look at is where X equals hydrogen. Now we're going to take the hydrogen electronegativity value and minus the carbon electronegativity value. The number that we arrive at has a plus or a minus, and this plus or minus is going to reflect the charge on the carbon atom. So let's look at this carbon-hydrogen bond specific case. So the hydrogen has an electronegativity value of 2.1. So 2.1 minus 2.5 gives us minus 0.4. That's to say the carbon atom is delta minus. So the hydrogen atom must have been delta plus. Not only this, it gives us a sense of magnitude of polarity. Now, theoretically, this is a polar covalent bond, but from a practical point of view, it's very often treated as a covalent bond. So 0.4 is a pretty small number. Let's look at our next example of an X element. And this is going to be oxygen. Things change here. So oxygen's electronegativity value is 3.5. So to do our calculation, 3.5 minus 2.5 gives us plus 1.0. So because of that plus, we now know that the delta plus is on the carbon. We can also see the magnitude is larger than the carbon-hydrogen bond. So the carbon-oxygen bond is really quite a polar covalent bond. The next case is the king of all electronegativity, and that's fluorine. So fluorine is the most electronegative atom there. Let's see what its effect is when we bond it to a carbon atom. So fluorine has a value of plus 4.0. So 4.0 minus 2.5. Firstly, what's the sign? The sign is plus. So delta plus is on the carbon atom. And secondly, the magnitude. Well, that's 1.5. It's huge. So this is a very polar covalent bond indeed. Our next case continues along the halogen elements. So we're going to look at chlorine. Chlorine has a value of 3.0. So 3.0 minus 2.5 is going to tell us the sign on the carbon atom. And that sign is plus. So the carbon atom is delta plus. Secondly, it's 0.5 in terms of magnitude. So it's not a very polar covalent bond, especially when compared to fluorine or compared to oxygen. Lastly, in this series, we're going to look at silicon. Things change up a little bit here, so it's kind of an interesting case. Silicon has an electronegativity value of 1.8. So 1.8 minus 2.5 gives us an answer of minus 0.7. So from the sign, we can see the carbon atom is going to be delta minus. And the magnitude is, it's okay, it's there, it's kind of a polar covalent bond, but it's not a very polar covalent bond. Not to the same degree as oxygen and not to the same degree certainly as fluorine. Next, we're going to look at magnesium. Now this is an interesting arrangement of atoms that becomes known as a Grignard reagent. A carbon-bromine bond, you can see, has a delta plus on the carbon if you do the calculation. We're not doing it here, but it doesn't take much to imagine. Now we can do a reaction where we insert a magnesium atom in between the carbon atom and the bromine atom. And you can see that has a dramatic effect on the carbon atom. We go from what was a delta plus carbon atom, and now if you do the calculation, you'll see that we arrive at a delta minus carbon atom. So this has turned the properties and the chemistry that we can do with that carbon atom on its head. The electrons shift by virtue of an induction effect. So this is a through bond effect, and we're pumping electrons onto the carbon. We see this in the case of magnesium, but also in the case of, for example, lithium. The same thing is going on. We're getting inductive donation of electrons onto the carbon atom. Nonmetals such as oxygen and chlorine inductively withdraw electrons away from the carbon, and so that's how we get our delta plus on the carbon in those cases.